Jai Hind, welcome to class of Analog and Digital Communication. We are going to talk about pulse modulation today. In the previous lecture, we have already seen the classification for pulse modulation, which includes pulse analog and pulse digital techniques. Under pulse analog techniques, we have studied about PAM, PWM and PPM. Now under pulse digital modulation techniques, we'll talk about PCM and delta modulation. So let's start with pulse code modulation. What is pulse code modulation? It is simply a conversion technique for analog signal into binary form, right? So when a digital signal undergoes pulse code modulation, it converts the analog information into a binary sequence of 1 and 0s. Through the demodulation process, we can again obtain back my analog signal. In pulse code modulation techniques, pulse code modulation techniques are used to produce a series of numbers or digits in binary form. Hence, this process is also called as digital modulation. The amplitude at that particular time of the signal sample is indicated by the binary codes. So, in PCM process, a sequence of coded pulses indicates the message signal. So, let's see how can I represent this. So, if this is my analog signal, when this is encoded in the form of series of encoded pulses, the output is called as PCM output. And according to the levels of the voltage value, I can assign it into binary bits, right? So let's see how it works. Before that, we have two types of PCM that we'll study as advanced form of PCM: adaptive differential pulse code modulation and adaptive differential pulse code modulation. In differential pulse code modulation, we use prediction techniques, and in adaptive differential pulse code modulation, we make the quantization step varying. We make our quantization step varying as per the input message signal. If the slope of the input is too high, we'll increase the step size, and if it is the slope is not too high, we'll decrease it. We'll see all that in detail. So let's start with PCM block diagram. This block diagram is of complete transmitter, channel and the receiver. At transmitter, what happens? When we have to convert an analog signal into digital form, there are three basic steps that we have to follow, which is sampling, then quantization and then encoding, right? So at my transmitter, I am using a sampler, a quantizer and an encoder. And we know that for my analog signal to be sampled, it has to strictly follow sampling theorem. So in order to prevent my signal from aliasing effect, I will be using low pass filters here, which can also be called as anti-aliasing filter. The concept of sampling has been discussed in previous lectures. So the input is my analog wave, and before passing it to a sampler, I'll pass it through a low pass filter. The job of this low pass filter will be to act as an anti-aliasing filter. What will a sampler do? My sampler will simply convert a continuous time signal into discrete time signal. That is, it will discretize my time domain. So it will generate such kind of samples depending on what kind of sampler we are using, whether we go with flat top sampling or instantaneous sampling or natural sampling, right? After sampling, I know that my signal is now discrete in time, but the amplitude part is still continuous. So my quantizer will do that job. It will discretize the amplitude domain as well. That means it will assign a particular level to a sample. Hence, we are reducing the number of we are reducing the infinite set of values into finite one in case of amplitude. So quantizer does that task for me. Now the final step will be converting those quantized values into binary sequences, and that is done with the help of an encoder. So encoding is the next step, right? Now what travels on air is my binary bits. So I have successfully generated binary bits. Now as if the channel provided to me is wired in mode, then simply my bits won't travel. I have to transmit some voltage levels, right? So in case of pulse code modulation, my analog signal is encoded as series of pulses, and that will be propagating via the channel. In the channel, I'll use couple of regenerative repeaters that will help me amplify the signal if it has lost some of its energy, and it will act for denoising as well, right? So regenerative repeaters, the basic job of a regenerative repeater is to amplify the signal which has lost some of its power and energy while traveling. And at the receiver, what happens? All those things that has occurred at transmitter that we need to undo. So the first circuit that we use at PCM receiver will be my regeneration circuit, right? My regeneration circuit will take the input which has traveled along the long distance of channel. Then the first thing that it will do is decoding, as the last step of the transmitter was encoding. So firstly it will do decoding. After that, this reconstruction filter will do the job of retrieving back the signal in a way that it undo the process of sampling and quantization. So my reconstruction filter helps me undo the process of quantization and sampling, and finally it reaches the end destination, right? So this is how my complete pulse code modulation block diagram looks like. Let's see working of each one, each block in detail. The transmitter section of a pulse code modulator circuit consists of sampling, quantizing and encoding, which are performed in the analog to digital converter section. The low pass filter prior to sampling prevents aliasing of the message signal, right? So I have discussed this already, that the low pass filter act as anti-aliasing filter here, right? How the basic operation takes place? The basic operation in the receiver section are regeneration impaired signals, decoding and reconstruction. These are the three basic tasks that has to be done at receiver side, right? That is regeneration of the signal, then decoding, and finally the reconstruction of the quantized pulse train. Following is the block diagram of PCM, which we have already discussed, right? Which represents the basic elements of both the transmitter and receiver section. This, right? What is the job of the low pass filter? My low pass filter eliminates the high frequency components, true, present in the input analog signal, which is greater than the highest frequency of the message signal, right? We know that before sampling I have to check that during the sampling, my sampling frequency must be greater than equals to twice the maximum frequency content of the message. So I have to check if some other signals whose frequencies is greater than the maximum frequency content of the message has got involved with the has got mixed, that has to be removed. For that purpose we are using low pass filter. This will help me avoid aliasing effect, right? Now next, what is the job of a sampler? This is the technique in sampling. Sampling is a technique which helps to collect the sample data at instantaneous values of the message signal. True. Sampling will convert my continuous time signal into discrete time signal so as to reconstruct the original signal, and sampling rate must be greater than twice the highest frequency component W. So here FM is denoted as W, right? What is the job of a quantizer? It is the process of reducing the excessive bits and confining the data, right? We discretize the amplitude domain as well with the help of quantizer. Now the sampled output, when given to the quantizer, it reduces the redundant bits. So quantizer will help me reduce the number of bits. Now next, what is the job of an encoder? The digitization of analog signal is done by encoder. The final digitization step, it will be done by encoder. It designates each quantized level by a binary code true. The sampling done here is sample and hold process, which has been discussed in detail in previous lecture, how sampling takes place. And in pulse amplitude modulation generation, we have discussed about sample and hold circuit in detail. These three sections, LPF, sampler and quantizer, will act as an analog to digital converter. A to D converter. What is it? What is in practical case? What is A to D converter? A to D converter consists of a sampler, a quantizer, and an encoder. Encoding minimizes the bandwidth used. True. What is the job of a regenerative repeaters? It increases the signal strength. The output of the channel also has one regenerative repeater circuit at the initial stage, It compensates for all the signal loss and reconstruct the signal, and it also increases the strength of the signal, right? Next block that we use is, let's give a look again. After regeneration circuit, we have a decoder. So what does decoder do? The decoder circuit decodes the pulse coded waveform to reproduce the original signal. This circuit acts as the demodulator, right? True. Reconstruction filter. After digital to analog conversion is done, the regenerative circuit and the decoder and a low pass filter is employed. This is called as reconstruction filter. This is to get the original signal, right? So this will undo the job of sampler and the quantizer. Hence, pulse code modulator circuit, it digitizes the analog signal, codes it and samples it, and then transmits it in the analog form. This whole process is repeated in reverse pattern to obtain the original signal. What are the advantages and disadvantages of my pulse code modulator signal? My PCM is mainly used in long distance communication. Here the transmitter efficiency is more, and it has it has better noise immunity as compared to other methods. So when we have to use for long distance communication, we do use pulse code modulation. If we talk about the efficiency, it has good efficiency. Even noise immunity is better, as we are sending the message in the form of coded pulses. And if I talk about disadvantages of PCM, here more bandwidth is required when compared to analog systems. PCM requires higher bandwidth, which is one of the major disadvantage. In this method, encoding, decoding and quantization of the circuit have to be done. This makes it more complex. All the steps undergoes, so this is somewhat a complex process. What are the basic applications of pulse code modulation? Where can I use it? It is used in telephony and in compact discs as well. So the wired telephone that we used to have earlier, before mobile phone came into existence, now also we have wired telephony that uses pulse code modulation. Encryption can be applied here. This is a kind of technique where it is easier to transmit via cable. In pulse code modulation, what happens? See, I have an analog signal. When I am representing it in the form of pulses, that means what I am generating finally is some voltage value, right? What I am generating is a voltage value. So when I need a wired link, that is a communication cable, then what happens? Through cable, I can transmit voltage values. So when I convert my analog signal into series of pulses, that is voltage values, and I have the channel which is wired cable, it is convenient for me to transmit. If I would have been using antennas for transmission, then I would again need a high frequency carrier. But if I have a wide cable for communication, then I will go with pulses. I hope I made the difference clear. One thing we need to take care of, when we are using wireless mode of communication, when two antennas are communicating, when I use a transmitting antenna and I use a receiving antenna, in that case, the signal has to be a sinusoid. But when I am using a line connection would carry voltage levels. So in that case, I will be transmitting pulses. So telephony, wired telephony, it's one of the major application of PCM which we use till date. And if I talk about a satellite transmission, yes, in satellite transmission as well, we use pulse code modulation. So, like I discussed earlier, let's go back to the previous slide and once again read it. As I can classify pulse code modulation in two types, which are the advanced version of pulse code modulation: differential pulse code modulation and adaptive differential pulse code modulation. In differential pulse code modulation, we use some memory element and we do modulation. Let's see how it is done. One of the disadvantage of pulse code modulation we just studied is it's require higher bandwidth. That is, too many bits against a particular message is generated. Now how to reduce it? That is a big question, right? If I want to reduce the number of bits corresponding to a particular message, then what do? I might use differential pulse code modulation. What it does? For the samples which are highly correlated, when encoded by PCM, they leave redundant information, isn't it? If I'm using highly correlated samples, that is, I use very closely spaced samples, so I have too much of redundancy. So why not reduce that redundancy so that I can communicate efficiently? So what happens in differential pulse code modulation? I may use some prediction circuit and that will help me predict the output, so I will not generate these many correlated samples. To process this redundant information and to have a better output, it is wise decision to take a predicted sampled value assumed from its previous output and summarize them with the quantized value. Such a process is called as differential pulse code modulation. Right? So we are using a prediction circuit, that is taking the decision that what it does, it assumes, see, a predicted sampled value assumed from the previous output and summarize them with the quantized value. Then I don't need such highly correlated samples. I'm using a prediction circuit to predict that. So I am reducing the redundancy here. So the transmitter would consist of a quantizer, a predictor with two summer circuits. This is how it looks like. So before that, I'll have a sampler, of course. After quantizer, I'll of course have an encoder. As these two blocks are similar, the difference I observe is in the quantization. So I have represented, this block diagram is used to represent the PCM, DPCM. So if I talk about the sampled input, I know the analog signal looks like this, and after sampling, I get XNTS, that is, which is the sampled version of XT. This is summation circuit. What I receive as another input is the predicted version of the sample. And where do I get it from? I get it from the predictor. And where does the predictor get input from? Predictor get input from the previous prediction and the quantized value, which is represented as UNTS. And what do I give input to the quantizer? Not the sample, but the difference of the present sample and its predicted version. That is the error signal. and here only error is quantized, and after quantization the quantized value is written as VNTS, is represented as VNTS. Here XNTS is the sampled input, X cap NTS is the predicted sample, ENTS is the difference of sampled input and the predicted output. It is also called as prediction error. So hence it is also called as prediction error. VNTS is the quantized output as discussed, and UNTS is the, what is UNTS? Here, this. UNTS is the predictor input, which is actually the summer output of the predictor output and the quantizer output, right? So this is how it works. So we are not actually quantizing every sample, but what we are quantizing is the difference of the sample and its predicted version, and hence this works in a way that it reduces the redundancy. If I talk about the DPCM receiver, it will consist of a decoder, a predictor and a summer circuit. Let's give it a look. This is how my DPCM receiver will look like. So to demodulate such signal, what do I use? I'll be using a decoder, right? And here again add for the receiver, I'll be using again a predictor circuit. Input to the decoder will be my binary bits, hence represented as BNTS, right? To this summer circuit, one of the input is the decoded version of the binary input that I received through the channel, and another input that I give is through the predictor circuit, which is the predicted version of my sample, right? And how do I get it? The output will be my UNTS, which is the same UNTS as used here, which is the predictor input, which is actually the summer output of the predictor output and the quantizer output. So this is how my receiver works, and I'll be successfully able to retrieve back my analog signal, right, after applying it to reconstruction filter and further demodulating it. The notation of the signal is the same as that of the previous ones as discussed. In absence of noise, the encoded receiver input will be same as the encoded transmitter output, and as mentioned before, the predictor here assumes a value which is based on the previous outputs, that is, it uses a prediction. The input given to the decoder is processed, and that output is summed up with the output of the predictor to obtain a better output, right? So that's it for today. We have discussed about pulse code modulation, and to overcome one of its major limitation, which is higher bandwidth requirement, what we use is a differential pulse code modulation. The transmitter and receiver block diagram for both PCM and DPCM has been discussed in detail. If we want to talk about adaptive pulse code modulation, in that case, one thing that actually varies is the step size of the quantizer. That will depend on the slope of the input wave. So that can be taken into detail in previous in the upcoming lectures. So that's it for today. Thank you. These are the references I've used.